The final thing we'll look at is finding uncertainties in the observables that we can look at. So I wrote this equation up previously, but the variance in a particular observable is given by the expectation value of the square of that observable minus the expectation value squared. Now, these are not the same, and let's look at how those are different. Right? The expectation value of x squared is the integral from 0 to a psi star x hat squared psi dx, whereas the expectation value of x squared is just the expectation value of x and the whole thing squared. Right? So these are slightly different from each other. So let's look at a specific example. What's the uncertainty in the position? X is the position. Right? If this were a classical object, we'd say 0. We know exactly where the particle is at all times. But in quantum mechanics, that's not true. And so we can go ahead and calculate this by using this, using this formula that we have. So in your homework, you'll find that the expectation value of x for a particle in a box is a over 2. And so we're just going to take that as a given. You'll work out, that exact value. So we can say that the second half of this, x squared, is just a squared over 4. And so we just need to find what is the expectation value of x squared. And so to do that, we have to go through and solve this, right? We have to plug this into an integral. So the expectation value of x squared is equal to the integral from 0 to a, square root of 2 over a, sine n pi x over a, x squared, and then same thing again. Okay, and so this is the integral that we need to solve. So we can, again, pull out our constants, and we'll have an integral from 0 to a of x squared sine squared n pi x over a dx. We can use an integral table to solve this. So x squared times sine squared. And we'll just get to the final solution. So we end up with a squared over 3 minus a squared over 2n squared pi squared. Okay, so that is, I'm skipping a bunch of steps there, but you can solve this on your own if you would like to. So then let's go ahead and look at the variance, right? So the sigma x squared. And that's, again, that is our expectation value of x squared minus the expectation value of x squared. So that's a squared over 3 minus a squared over 2n squared pi squared. And then all of that minus a squared over 4, right? And that's what we said is equal to this. Okay, so we can go ahead and make a common denominator here. We'll end up with a squared over 12 minus a squared over 2n squared pi squared. And then we can rewrite this slightly as a over 2 pi n squared times pi squared n squared over 3 minus 2. Okay, and so that is our uncertainty in our position, right? It depends on n. The larger n gets, the bigger our uncertainty will be. And sigma x is the square root of that, right? So this was the variance. Sigma x is equal to a over 2 pi n times all the stuff on the right square root. So pi squared n squared over 3 minus 2 raised to the 1/2. Okay, so what this tells us is that we don't know the exact position of the particle, right? So we know probabilities, but we don't know exactly where it is in the box. We can do this with the momentum as well. I won't go through all the calculations for the momentum. It's in your textbook. But the But the important thing is that once we go through and find the uncertainty in the momentum in the momentum ends up being sigma p is n pi h bar over a. If we take sigma x times sigma p, we end up with h bar over 2 pi squared n squared over 3 minus 2 raised to the 1/2. Right, so these two parts will cancel out and we end up with an h bar over 2. And what we see is that what's present here is always going to be greater than 1. And what that tells us is that we can actually calculate the uncertainties, and this satisfies the uncertainty principle. Right? This will always be greater than h bar over 2. So we have a mathematical way of showing that and showing that we all are always going to have something greater than h bar over 2, and this satisfies the uncertainty principle that we talked about earlier.